Hello, these are the solutions to AP Physics Suggested Problem Set 4.1, which are forces from Chapter 5. So the first problem is an apparent weight problem. Here's a hint. Which is essentially going to be an elevator problem for us. So we have a 550 Newton physics student standing on a scale in an elevator supported by a cable. So doing a quick sketch of this situation, we have an elevator, we have a person, we have a scale, and we have an elevator that is also supported by a cable. So the student, I'm going to say the weight of the student, is equal to 550 newtons. The combined mass of the student and elevator is 850 kilograms. So that's going to be M total. And as the elevator starts to move, the scale reads 450 newtons. So I'm just going to write scale reads 450 newtons. So what does that tell us? Well, if the scale reads 450 newtons, that is actually reading the normal force on the student. So what's actually happening here? Well, if we sketch a free body for this situation, we have the student as a dot with gravity pulling him down, which is equal to, in this case, 550 newtons. And then we have a scale reading, and it reads 450 newtons. Well, that's less than the force of gravity, so I'm just going to go ahead and write Fn equals 450 newtons. And that's in the upward direction. So A says, find the acceleration of the elevator. Well, the acceleration of the student is equal to the acceleration of the elevator. So if I find the acceleration of the student based off of his free body diagram, I should know the acceleration of the elevator. So sum of forces in the y direction for this student, so I'll say this is the student, is going to be the normal force minus the force of gravity, and that's equal to the mass of the student times his acceleration. So for us, we need to know the mass of the student. Well, I know the weight of the student, and therefore the weight of the student would be equal to his or her mass times the acceleration due to gravity. So I need to find that mass. So that'll just be the weight divided by g, or in this case, 550 newtons divided by, we'll go ahead and use 10, and we'll go ahead and use the gravitational field strength units, which are newtons per kilogram, because that makes my units work out very nice. So easy math here gives me a mass of 55 kilograms for the student. And so my acceleration is just going to be 450 newtons minus 550 newtons over the mass of 55 kilograms. And so my acceleration should be a negative, and I need to plug this in my calculator because it's not quite that simple, a negative 1.82 we will say, and that will be meters per second per second. So this makes sense. We are accelerating downward because the scale is reading something less than his actual weight. B says, well, what is the acceleration if the scale were to read 670 newtons? So the only thing that changes here is that my normal force is now not 450, it is actually 670. So my sum of forces is slightly different when I substitute, right? It's still normal minus the force of gravity is equal to the mass times the acceleration. And therefore, my setup for the acceleration would be the same. So I will have 670 newtons minus the 550 over 55 kilograms. Sorry, that should be a 5, or a more legible 5 rather. And my acceleration then would be 2.18, and this time it's positive because the scale is reading something higher than his normal weight. So C says, if the scale were to read 0, should the student worry? Well, let's see. If your normal force is 0, right, the scale reads 0, then that means that you are accelerating downward somehow, right? the scale were to read 0, if this normal force were to equal 0, that means you're accelerating downward very fast. How fast? Well, your acceleration would have to be equal to that due to gravity. So it would be equal to negative g, or negative 10 meters per second squared. At that point, I think you should worry, because you are in free fall. So free fall in an elevator is generally considered to be a bad thing, because at that point, your elevator is probably not connected to anything. So at that point, I think they should worry. Now D says, what is the tension in the cable for parts A and C? So for part A, I know that I have, so this is part D. So I want to know the tension in the cable. So in this case, I want to know the force of gravity on the elevator. So this is now for the elevator. And there is some tension acting on it. So that's force tension. So my sum of forces for this setup is going to be the tension minus the force of gravity is equal to the total mass, I'll just do mt, times the acceleration, we can say, of the elevator or the student. It doesn't matter. They should be the same. So solving for my tension force, I'm going to have the total mass times the acceleration from part A plus the force of gravity on the elevator. So the force of gravity on the elevator is simply going to be the total mass times, the total mass times g. So what does this look like? Well, that's going to be the total mass, which we wrote as 850 kilograms. Should say FT. 850 kilograms times actually the sum of these accelerations. So from part A, my acceleration is negative 1.82 plus g. So this time it's just g. It's not going to be negative on extra here. So plus 9.8. Or I probably should continue to use 10, actually. Always be consistent with what you end up using for your acceleration due to gravity. So for us, that'll be 850 times 10 minus 1.82, which is a tension force of 6,953 newtons. And this is from part A. And then for part C, well, if we're in free fall, then that means the only force acting on it is the force due to gravity, which means that your tension force should equal to 0, right? Because free fall implies that your only force acting on it is the force due to gravity. For problem 527, a stockroom worker is pushing a box with a mass of 16.8 kilograms on a horizontal surface with a constant speed of 3.5 meters per second. So let's do a quick sketch. So here's my horizontal surface. Here's my box. My box has a mass of 16.8 kilograms, and it's moving with some constant speed of 3.5 meters per second. So I'm actually going to go ahead and indicate that that's a constant speed because that's an important fact. And I guess we'll go ahead and say that there is a person pushing this. So we'll do a nice little stick figure sketch of a person pushing. And so the coefficient of kinetic friction between the box and the surface is 0.2. So I'm going to go ahead and write mu k is equal to 0.2. Now A says, what horizontal force must the worker apply to maintain the motion? So that means we need to analyze forces. So let's sketch a free body for this box. So the forces that act on it will be force of gravity, most obviously, which would be equal to mg. A normal force, which I'm going to go ahead and say is a good guess, will be equal to the force of gravity. And then we have a force pushing to the right. So this is the horizontal force that the guy is doing. So we'll say this is Fp. And then there is a friction force resisting that motion. So I have a friction force going to the left. So my sum of force equations will be, I should probably do x first. My sum of force equations will be in the x direction, the pushing force minus the force of friction is equal to mass times the acceleration in the x direction. Now, because my velocity is constant, this acceleration should be 0. Leaving a little room, my sum of forces in the y direction will be normal force minus the force of gravity is equal to mass times acceleration in the y. Well, I'm pretty sure my box is not floating up off the ground, so my y acceleration is also 0. So the next step I'll say is, all right, force push is therefore going to be equal to the force of friction. And the force of friction, remember, is equal to mu, in this case mu k, times the normal force. Right? Just in case you've forgotten, force of friction is going to be mu times normal. For us, this is kinetic friction, so this would be mu k specifically. From our y, we have Fn is equal to the force of gravity, which is equal to mg. So when I plug this in to my first equation, I'll see that my pushing force is actually going to be equal to mu k times mg. So this pushing force for this situation would be 0.2 times my mass of 16.8 kilograms times g, which in this case will be, we'll go ahead and use 10 again. Why not? 10, and we'll say newtons per kilogram to make my units nice and simple to deal with. So this pushing force, when I plug it into my calculator, is going to be a whopping 33.6 newtons. Now B says, if the force is removed, how far will the box slide before coming to rest? So I need to therefore know my force of friction, because my free body diagram changes such that I still have a normal, I still have gravity, but I no longer have a pushing force. So my only force in the horizontal is my force of friction. Therefore, my sum of forces in the x direction would just be the negative force of friction is equal to my mass times my acceleration in the x direction, which is no longer 0. So because my force of friction is going to be mu times Fn, therefore, my force of friction is going to be, in this case, negative mu k times mg, which will be equal to max. So I can see that my masses will cancel in this case. My acceleration in the x direction is just going to be negative my coefficient of friction times g. So substituting here, we have negative 0.2 times 10 meters per second squared. And this math is pretty easy, but it would be negative 2 meters per second squared. So that's my acceleration. But the question asks, how far does it go? So I'll need to use my equations, my kinematic equations. I know that V initial is 3.5 meters per second. The question asks if I can figure out how far it goes before stopping. So V final will be 0. I just found my acceleration, so these four variables together seem to imply that I'm going to want to use the third kinematic equation, which, if you've forgotten, is v squared is equal to v naught squared plus 2a delta x. Or rather, these are all for the x direction. So v final is 0, so I'll make that simplification. And rearranging this to solve for delta x would give me v naught squared over 2a. And in fact, this is going to be negative v naught squared. So my substitution will be negative 3.5 meters per second squared over 2 times negative 2 meters per second squared. So my change in position, my displacement in this case, is going to be 3.06 meters, rounded to 3 significant figures. All right, so the solution of 5.33 has 2 boxes on an incline. So first, I'm going to take these 2 boxes and I'm going to treat them as a single mass because they are moving together, at least for part A. So my free body diagram for part A should look like this, where I have a force pulling up and to the right. I have a force of gravity acting down. I have a normal force up and to the left. Now, the way the angle is defined is we'll define it right here as theta. So that would be right here. So this is my pushing force. Now we also have a coefficient of friction between these two boxes in the plane, and that is 0.444. We also have a coefficient of static friction between the two boxes, which is equal to 0.8. So we are moving at a constant speed, and so since we have that friction, we have a resisting force. So we're moving, we're going lower, so our speed is actually down and to the left. So if our speed is in this direction, that means that my friction force is going to be opposite that. So my friction force is actually up the ramp. So I have two forces up the ramp. All right, so the angle theta here is based off the geometry of the triangle. So theta is going to be the arctangent of 2.5 over 4.75. And so theta in this case is going to be 27.76 degrees. And that's going to be used later. So now we need to figure out what force we need in order to do a single bit of constant velocity motion. So I'm going to start by rotating my set of axes here so that they align with more forces. And so I'm rotating by an angle theta this direction counterclockwise. So that means that this angle now is theta. So I actually have two components of force. I have a force of gravity that direction and a force of gravity in that direction. And so now, when I sum my forces, this is what they should look like. In my new x direction, which we'll say is down the ramp, I would have only a negative force of friction and a negative pulling force, or pushing force, pulling force in this case. And that should be, and then in the positive direction, I have a component of the force of gravity, which is going to be, in this case, the sine of theta is equal to ma in the x direction. So just going to simplify this a little bit. So I have mg sine theta minus mu k, which is over here, times the normal force, minus force push is equal to max, which is actually 0 because we're moving at a constant speed. So I'm going to go ahead and say that that is 0. So there's my x direction. In the y direction, I have normal force minus the cosine component of force of gravity. So it'll be Fg cosine theta is equal to ma in the y, which is 0. So a little simplification here, I can say normal force minus mg cosine theta is equal to 0, or just straight up normal force is equal to mg cosine theta. And so I can take this and plug it back into my x equation. So pulling that down, what I end up seeing is mg sine theta minus mu k mg cosine theta minus fp equals 0. So my pulling force is going to be just, actually pull some things out here. It's going to be mg times the sine of theta. Ooh, actually I need to do, oh no, that's right. Sine of theta minus mu k times the cosine of theta. So substitution looks something like this. The masses together would be an 80 kilogram mass. So I have 80 kilograms times g, which we'll just use as 10 newtons per kilogram, times the sine of 27.76 degrees minus the 0.444 times the cosine of 27.76 degrees. So my pushing force, or pulling force in this case, is going to be, looks like 58.3 newtons in order to have constant speed. So B says, what are the magnitude and direction of the friction force on this ramp? So for part B, I know the pulling force, And I can just go back in here and say, all right, force of friction is going to be equal to mu k times mg times the cosine of theta. So that friction force is going to be 0. Oh, I'm sorry, this should be on the upper box. So let me back that up a second. So in the upper box, we have a different free body diagram. So we have force of gravity pulling down, then we have a normal force this direction, and then we have a friction force. So which way would the box tend to move? Well, if we're trying to stay up on top of this, my friction force is actually up and to the right. Right? If you think about it also from so this is the top box. The bottom box is a little weirder because you have force of gravity, of course. You also have a normal force from the surface. Then you also have some kind of force pushing down on the box from above, right? So you have actually a friction force that is from the top that is pushing down the ramp, and then you have a friction force from the ramp pushing up on the other box. So this is a little weird, but we're going to stick with this here. And so we also, actually, I guess, should recall that there is some amount of force from the force of gravity above it. So this is a very odd free body diagram. Anyway, so for our top box, we have new sum of forces. So I will set up my axes. In this case, when I rotate, this is again theta, which means that this is also theta. So my sum of forces will look like in the x direction, which is the direction it was going to try to move. We have the force of gravity for the top box times the sine of theta minus the force of friction is equal to max, which is 0. So this simplifies to mg sine theta minus mu s times normal. So I don't actually have to do that, right? I can just keep it as force of friction. So I can say mg sine theta minus the force of friction is equal to 0. Therefore, the force of friction would be equal to mg times the sine of theta. So my force of friction then is just going to be the 32 kilograms mass times the 10 newtons per kilogram times the sine of 27.76 degrees. So my force of friction then is actually quite easy to get, which ends up being 149 newtons. So question 5.34 has a linked mass system of two different blocks, block A and block B. Once block B is set into motion, the whole system moves at a constant speed because they must move at the same speed because they are linked together. So A says calculate the coefficient of kinetic friction between block A and the tabletop. So I'm going to draw two free body diagrams to get started here. So block A has the force of gravity pulling down, so we'll just say that's FGA, which is going to be equal to 45 newtons, as described here. We have a normal force pushing up. We have a tension pulling to the right. And then we have a friction force pushing backward to the left. For block B, my free body diagram would simply be force of gravity on B, which is 25 newtons. And pulling upward, we actually have the tension force. So, what does that mean? Well, from my second free body, sum of forces in the y direction, which would just be tension minus FGB, is equal to MAY, which is 0 because I'm moving at constant speed, tells me that my tension force is simply equal to 25 newtons. Therefore, when I go back into A, I have in the x direction, force tension minus force of friction equals MA in the x direction, which is 0. And so I can rewrite this as tension force equals mu k times normal force. So I do need to know my normal force. So that means in my y direction, I have the normal force acting on A minus the force of gravity on A is equal to mass times acceleration in the y direction, which is 0. Then my normal force on A is going to be equal to my force of gravity on A, which is 45 newtons. So I can take my original equation here and say that mu k will be equal to the tension over normal force on A, which is going to be 25 newtons over 45 newtons. So mu k in this case is just 0.556 or 0.56 we'll say. And there's no units to that. Now the second part says if a cat that also weighs 45 newtons falls asleep on top of block A, what will the acceleration of block B be? So part B here, we're going to assume that mu k is going to stay the same from part A. So what changes? Well, my free bodies essentially are the same, except block A now has, in addition to the force of gravity, also has the force of some cat pushing down on it. So there's going to be a different friction force related to the tension. And then we have a normal force acting upward. So how does this end up working? Well, we have, so this is block A. Block B will be the same. It'll be force of gravity and then normal force. So that's not normal, tension. So that's B. Tension we can be the same, right? Tension is the same throughout this chord. So what ends up happening? Well, for block A in the x direction, now I have tension minus force of friction equals max. So I do have a non-zero acceleration in the x now. And I want to find that. So my acceleration in the x is going to be my tension minus my force of friction over the mass. So what ends up changing in this? Well, tension is actually the same. The tension is still going to be 25 newtons because my free body diagram for block B has not changed. So my tension is still 25 newtons. My force of friction, however, is going to change. So I have actually AX is equal to tension minus, actually I can go ahead and plug in the 25 since I know that. 25 minus mu k times normal force over m. So the question is, what changes with Fn, my normal force, and m? Well, mass is actually now the total mass of the cat and the block. So what will that be? Well, it's going to be the total weight divided by g. So that means I'm going to have 45 plus 45 newtons divided by 10 newtons per kilogram. So my total mass in this case is actually 9 kilograms. Similarly, my normal force, which comes from my sum of forces in the y direction, is going to be a little different. So that's going to be the normal force minus the force of the cat minus the force of gravity on the block is equal to may, which is 0. So my normal force is actually going to be the sum of these two forces, the 45 newtons for the cat and the 45 newtons for the weight. So my normal force is actually 90 newtons in this case. So what ends up happening here is my acceleration will be 25 minus mu k, which I found to be 0.56, times my new normal force of 90 newtons over my mass of 9 kilograms. So my acceleration in this case is going to be a negative 2.82 meters per second per second. So if this cat gets on the box, then we will actually be slowing down. So for question 5.37, we have two crates connected by a rope on a horizontal surface. Crate A has mass ma, so I can just write that below that. And B, surprise, surprise, has mass B. The coefficient of kinetic friction between the crate and surface is mu k. So this is a symbolic problem in case you couldn't tell. And they're pulled to the right by some constant, well, they're pulled to the right by some force F at a constant velocity. So we want to draw one or more, hint, hint, more, free body diagrams to calculate something in terms of the two masses and the coefficient of friction. So I want to calculate the magnitude of F, and then I want to calculate the tension between the two blocks. So the first thing I'm going to do is I'm actually going to start by drawing just one free body diagram, and that's for the whole system, right? So this is actually going to be the mass A plus mass B. So I have some force going to the right, and that's F. I have some normal force acting upward. I have some force of gravity acting downward, and that's with both masses. And then I have a force of kinetic friction resisting motion to the left. So my sum of force equations will look as such. In the x direction, I'll have F minus the force of friction is equal to ma in the x direction. And that is 0 because we're moving at a constant velocity. So just to simplify this and rewrite it, I have Ff, which will be mu k times some normal force equal to 0. Now for the y direction, I have the normal force minus the force of gravity is equal to ma in the y, which is 0. And to rewrite this, I have normal force minus, and I'm actually going to write it as ma plus mb times g is equal to 0. So symbolically, from my y direction, I can say the normal force is equal to the sum of the two masses times g. And I can take that along with my x direction, which says F is actually equal to mu k times normal force, and say that mu k times Fn is actually mu k times the sum of the masses times g. And that's it for part A. And we did that, of course, with one free body diagram because the whole system must move together. Now for B, I'm actually going to draw two free body diagrams. So I have a free body diagram for mass A and a free body diagram for mass B. A little too out of the way. So how does this work? Well, mass A has force of gravity, which will be mag, and for mass B, same deal. It's going to be mass B, though. Then we have some kind of normal force, so I'll call Fna, and then this one will be Fnb. And then I have a force of friction, of course, acting to the left. And the same thing, some other force of friction for B. And then for block A, I have some tension pulling to the right. So I'll say this is force tension. Now, because of the way the ropes are connected, I actually have a tension force on B acting to the left. So I don't know how strong this is, but I'm just going to do that for the sake of space. And then I have some force F to the right. So the question I want to find is the tension in the rope connecting these. So what I'll do is I'll say for the leftmost free body, my sum of forces in the x would be tension minus force of friction on A is equal to max for A, but this is 0. We're not moving at an accelerated rate. So I can just say tension force is equal to mu k times normal force on A. Now for the y direction, I have normal force on A minus mag is equal to may, which is 0. So my normal force A is equal to mag. So it actually makes this really simple, where I can say the tension force is actually just equal to mu k times mag. And those are all things I can write this in terms of, so I don't actually need to go any further. For question 5.38, we have a box with a mass m dragged across a level floor. So I'm going to start sketching this. So box with mass m dragged across a level floor with a coefficient of friction that is mu k, and we're pulled by a rope that makes an angle theta above the horizontal, so I'm going to do that, with some force of magnitude F. So, in terms of m, mu, theta, and g, obtain an expression for the magnitude of the force required at constant speed. So V equals constant. So, I'm going to start with the free body. My free body looks like the following. I have force of gravity down, which is mg. I have normal force upward. I have a force of friction to the left, resisting my motion. And then I have a force F up at some angle theta with the horizontal. So I don't need to do any rotating axes here because I have three forces aligned with my normal axes. And so now I can just go through and write my sum of force equations. So in the x direction, I have F cosine theta minus the force of friction is equal to mass times acceleration in the x, which is 0 because we're at constant speed. So I can just say F, which I'm solving for in the end, is going to be F cosine theta minus mu k times normal equals 0, which rearranges to F is equal to mu k times normal force over cosine theta. Now, for the y direction, I have normal force plus F sine theta minus mg equals may, which is 0. And so I'm going to solve this for, we'll go ahead and say F. Not F, Fn. So my normal force is going to be equal to mg minus F sine theta. So now I can substitute this back into this equation, and I see that F will be equal to mu k times mg minus F sine theta all over cosine theta. So I actually still need to solve for F here, which means I need to do a little bit of algebra. So I would say this is mu k times mg minus mu k F sine theta, and then both of these would be divided by cosine theta. So the reason I'm doing that is I can simplify this and say I have mu k mg over cosine theta minus mu k F tangent theta. So I can actually move F, or move this term back to the other side. So I had F plus mu k tangent theta equals, times F. I should put an F here. Pardon me, I hit the wrong button. And just try this whole writing again. Mu k F tangent theta equals mu k mg over cosine theta. And so factoring F out of here, I have F times, and then dividing by what's left, I'm going to have F equals mu k mg over cosine theta. And I'm dividing by, so I'm just going to multiply by 1 over, 1 plus mu k tangent theta. So this is a little disgusting, but exactly what we want. So you could go through and simplify this more if you really wanted to. What would that look like? Well, I would have still mu k mg on top, but in the bottom I would have cosine theta plus mu k sine theta. So either one of these is fine, I would say. Now part B says, knowing you're studying physics, a CPR instructor asks how much force it would take to slide a 90-kilogram patient across a floor at constant speed by pulling him on him at an angle of 25 degrees above the horizontal, and you find that UK is 0.35. So this is basically just taking everything we just did and plugging numbers into it. So for B, I can write that M equals 90 kilograms, theta equals 25 degrees, mu k equals 0.35, and so I can take my result and substitute those values. So the force would be equal to 0.35 times 90 kilograms times, we'll do 9.8 this time, meters per second squared, over cosine of 25 degrees plus 0.35 times the sine of 25 degrees. So this is really just to illustrate the power of the symbolic solution. So plug this into your calculator, and I get a force of 341 newtons. All right, so for question 5.60 or 560, we have an archaeologist crossing between two rock cliffs, going hand over this rope. So he stops in the middle of the rope, and we want to know what's going on with the tension in these ropes. So I'm going to draw a free body diagram for this archaeologist where he touches the ropes right here. So that free body diagram will look like this. So he'll have force of gravity pulling down, which will be equal to mg. And then we have two tensions. We have a tension to the right and up, and a tension to the left and up. And both of these tensions are at an angle theta with respect to the horizontal. So we know that the mass of this person is 90 kilograms, and we know that force tension max is equal to 2.5 times 10 to the fourth. So A asks, what is tension if theta is equal to 10 degrees? So when we go through our free body diagram and sum forces, we see that in the x direction, the sum of forces would be force tension times the cosine of theta minus force tension times the cosine of theta equals ma in the y, which is 0. So this is pretty telling. Basically, it's just saying, like, if these were two different forces, they would be equal to each other. So from the y direction, however, we have the situation where we say that force tension times the sine of theta plus another force tension times the sine of theta minus mg is equal to mass times acceleration in the y, which is 0. So if this is the case, then we can say that 2 times force tension sine theta is equal to mg, or, just to get to the end, force tension is equal to mg over 2 times the sine of theta. So we can plug in some values for this. We have a mass of 90 kilograms. We have a g of 10 meters per second squared over 2 times the sine of our angle for this part of 10 degrees. And so we take this and plug it into our calculator, and we get that the tension is 2,590 approximately, I'm going to round, newtons. So that's the tension in each rope in this case. Now, the question is, what is the smallest value theta can have and not break the rope? So how do we go about doing this? Well, since we know that Ft max, so this is part B, Ft max is equal to 2.5 times 10 to the fourth, or 25,000. Then what we have is a situation where we can use this same result, because we can say that sine theta, so we're coming from here, is equal to mg over 2 times force tension. And so our theta max will be equal to the arc sine of mg over 2 times our tension max. So theta, in this case, will be the arc sine of 90 kilograms times 10 newtons per kilogram over 2 times our tension max of 25,000. Should be times 10 to the fourth. Yep. And that's newtons. So my theta max in this case, if I go into my calculator, actually gives me an angle of 1.03 degrees. So I should say, I guess I messed up. This should actually be a theta minimum, not a maximum. So basically what's happening here is the reason our angle is minimized is because in order to have a really high tension, we're pulling the string extremely taut, or the rope extremely taut. So there's a lot of force in the rope, and that's actually going to minimize this angle because our string will flatten out, our rope will flatten out if there's a lot of tension in it. For the last problem in this set, we have 5.65, where we have a ball that is attached to a string and resting against a wall. So this string is 30 centimeters, or this wire rather, and the ball has a diameter of 32 centimeters. So I'll just draw right on this for a second. So the diameter is 32 centimeters, and there's a mass for this of 45 kilograms. So A says draw the free body diagram for the ball. So here's my ball. So sorry, A. So my ball has the force of gravity acting downward on it, which is equal to mg. And then we have the wire pushing up this way, and it has some tension in it. And then we also have a normal force, and so the normal force acts perpendicular to the surfaces, so our normal force goes off to the left. Now, I need to kind of define an angle here, so in order to figure out that angle, I need to do a little geometry. So if this wire goes through the center, then that means that I have a triangle essentially formed here between the radius, which is 16 centimeters, and then this distance here, which is going to be 16 centimeters plus 30 centimeters. So this distance right here will let me get this angle. So let's call this angle alpha. So the sine of alpha will be equal to, in this case, the 16 centimeters over 16 plus 30, which is 46 centimeters. So my angle alpha is actually going to be the arcsine of that, which would give me an angle of about 20 degrees. So I'm going to write 20.35 degrees at this point. So that's this angle right here. That's alpha. Now, I want to find the tension in the wire. So to do that, I'm going to sum my forces in both directions. So I have tension force times the sine of alpha minus normal force equals ma in the x, and it's just sitting there, so that's 0. So I can say that my tension force is going to be equal to my normal force over the sine of that angle. Then, in order to figure out my normal force, I do sum of forces in the y, which will be force tension times the cosine of alpha minus mg, which is equal to may. And so it actually turns out that my tension force is not going to be easily found this way, but I'm actually going to be able to say that my tension force is mg over the cosine of my alpha. So that tension force is going to be 45 kilograms times 10 newtons per kilogram over the cosine of my 20.35 degrees. So the tension in that wire is going to be about 480 newtons. Then, since I already did this part, I can pull it over and say that, all right, normal force is actually equal to Ft times the sine of alpha. So, for me, that will be 480 newtons times the sine of 20.35 degrees. So my normal force, here for part B, is going to be 480 times the sine of 20.35 is actually 167 newtons. So this is not a very difficult problem, but it is worth doing a lot of these with some additional geometry considerations.